The quantum nature of electron energy. Every molecule dissolves. You, reading this right now, simply wouldn't exist. Why classical physics completely fails? Here. What if everything your physics teacher taught you was beautifully correct, but only for the big, slow, visible world and catastrophically wrong at the atomic level? Classical physics, the brilliant framework built by Newton and Maxwell, predicted something terrifying, a charged particle moving in a circular path, like an electron orbiting a nucleus, must radiate energy. It must spiral inward. It must crash into the nucleus within a fraction of a second. By classical calculations, every atom in the universe should have already destroyed itself billions of years ago. The fact that you're sitting here, breathing, thinking, proves classical physics missed something enormous. Scientists in the early 1900s faced this nightmare contradiction. Their equations were perfect for planets and cannonballs, but suicidal for atoms. The electron simply refused to obey. It kept orbiting. It kept existing. It laughed at Maxwell's equations. And that defiance, that stubborn, magnificent refusal to spiral inward, forced an entirely new branch of physics to be born. Quantum mechanics didn't emerge from curiosity alone. It emerged because reality demanded a completely different explanation, the wave nature of the electron. What if the electron isn't actually a tiny ball spinning around a nucleus, but something so weird, so fundamentally strange, that calling it a particle is almost an insult to its true nature? Louis de Broglie proposed something that sounds like science fiction. Matter has wavelength. Electrons aren't just particles, they behave like waves. And here's where it gets absolutely mind-bending. For a wave to exist stably around a nucleus, it must fit perfectly, like a snake biting its own tail, forming a complete, unbroken loop. If the wavelength doesn't fit perfectly, the wave interferes with itself and destroys itself. Only certain orbits, certain energy levels allow the wave to survive. This is why electrons don't spiral inward. There's no in-between orbit where the wave can sustain itself. The electron isn't choosing to stay in its orbit out of some loyalty to the atom. The wave mathematics simply forbids any other option. The electron exists where waves can survive. Everywhere else is mathematically, physically, absolutely forbidden. That's not philosophy, that's the architecture of reality itself. The Pauli exclusion principle, nature's most powerful law. What if the reason solid matter feels solid, the reason your hand doesn't pass through this table, the reason stars don't instantly collapse, all comes down to one single ruthless rule that electrons follow without exception? Wolfgang Pauli discovered something extraordinary. No two electrons can ever occupy the same quantum state simultaneously. Ever, not sometimes, not usually, never. This sounds simple until you realize its implications are universe-shaping. Because of this principle, electrons are forced to stack into different energy levels. They cannot all crowd into the lowest energy state. They must occupy progressively higher levels, like people forced to sit in different seats in a stadium. This stacking is what gives atoms their size, their shape, their chemical personality. It's what makes iron different from gold, what makes carbon able to form DNA. Without this principle, all electrons would collapse into the lowest orbit, all atoms would be identical, chemistry would be impossible, and life could never exist. One rule, no exceptions. And because of it, the universe has structure, diversity, and you. Heisenberg's uncertainty principle and zero-point energy. What if I told you that even in absolute zero temperature, the coldest possible state in the universe, electrons are still moving, still vibrating, still absolutely refusing to sit still? This isn't a measurement error. This isn't experimental imprecision. This is the universe's deepest secret. Heisenberg's uncertainty principle states that you can never simultaneously know both the exact position and exact momentum of an electron. If an electron were truly at rest, perfectly still, perfectly located, you would know both perfectly. But the universe doesn't permit that. The more precisely you pin down an electron's position, the more wildly uncertain its momentum becomes. So if an electron tried to stop, tried to fall into the nucleus and just sit there quietly, its position would be perfectly known, violating the uncertainty principle catastrophically. The universe responds by giving the electron irreducible, unavoidable motion called zero-point energy. The electron cannot stop moving because stopping would require the universe to break its own fundamental law. The electron's restlessness isn't a flaw. It's the universe protecting its own logical consistency. The stability of matter and why this changes everything. What if the entire technological civilization, your smartphone, the internet, nuclear energy, medical imaging, solar panels, everything, exists only because electrons stubbornly, magnificently refuse to lose their energy? The stability of the electron isn't just an interesting physics curiosity. It is the single most consequential fact in the physical universe. Because electrons maintain stable energy levels, atoms are stable. Because atoms are stable, molecules form. Because molecules form, chemistry happens. Because chemistry happens, biology happens. Because biology happens, you happen. Every second of your life is a direct consequence of this quantum stubbornness. And when we finally understood why electrons behave this way, when quantum mechanics gave us the mathematical tools to predict electron behavior, we didn't just satisfy scientific curiosity. We unlocked transistors, lasers, MRI machines, solar cells, and quantum computers. The most practical, world-changing technologies in human history were born from understanding this one beautiful, bizarre fact. The electron never loses its energy. And because of that simple, stubborn truth, the universe is magnificently, gloriously, impossibly alive. What if the most important rule in the entire universe, the rule that stops every atom from collapsing, the rule that makes your body possible, the rule that holds stars together and keeps galaxies from dissolving into nothing? What if that rule is something so bizarre, so completely backwards from everything your common sense tells you, that the moment you truly understand it, your entire picture of reality shatters and rebuilds itself into something far more beautiful and far more strange than you ever imagined possible? Here's the thing. Electrons never lose their energy. Never. Not slowly, not gradually, not even a little bit. And for centuries, the greatest minds in science looked at that fact and said, "That's impossible. That violates everything we know. Physics itself says it cannot happen." And yet, it happens. Every single moment, inside every single atom, inside every single cell of your body right now. So what is the universe doing? What secret is it hiding inside the heart of matter itself? Because the answer, the real answer, doesn't just explain electrons. It explains why anything exists at all. Stay with me, because by the end of this, you will never look at the world the same way again. What if I told you that the ground beneath your feet, the air filling your lungs, the blood moving through your veins right this moment, all of it exists because of one single, stubborn, absolutely non-negotiable fact about the tiniest thing in the universe: an electron never loses its energy. Now, I want you to pause on that, because your instincts, those beautiful, reliable instincts that help you navigate the everyday world, are about to be completely, gloriously wrong. And being wrong in the right direction is how all the greatest discoveries in history have happened. When you push a ball, it slows down. Friction takes its energy. Air resistance steals it away. Everything in your experience tells you that moving things eventually stop. Energy gets lost. Machines wear out. People get tired. That's just how the world works. That's just physics. Except it isn't. Not at the deepest level. Not where reality is actually built. Let me take you somewhere most people never go. Let me take you inside the atom. Imagine you're an electron. You're moving, circling around a nucleus, doing what electrons do. Now, according to the most successful physics ever developed up to the early 20th century, the physics of Maxwell, the physics of Newton, the beautiful, elegant classical physics that correctly describes everything from planetary orbits to electrical circuits, you should be losing energy, rapidly, catastrophically, because you're a charged particle moving in a curved path. And Maxwell's equations are absolutely mercilessly clear on this point. A charged particle accelerating in a circular path radiates energy. It must. The equations demand it. So you should be spiraling inward, losing energy with every loop, falling toward the nucleus faster and faster until, in less than 100 millionth of a second, you crash into it. And that means the atom destroys itself almost instantly. That means every atom in the universe should have collapsed long before stars formed, long before planets cooled, long before the first molecule of anything interesting was ever assembled. And yet, here you are, here I am, here everything is. The universe looked at Maxwell's equations, completely correct in every other context, and said, not today. So what went wrong? Or, more precisely, what did we get wrong? The answer starts with something that, the first time you hear it, sounds like a poet trying to do physics. But stay with it, because it's not poetry. It's the actual structure of reality. Matter has wavelength. I know what that sounds like. But here's what it means. An electron isn't just a tiny ball flying around a nucleus like a miniature planet. It's also a wave, simultaneously, always. Not sometimes a particle and sometimes a wave, both always at once, in a way that doesn't have a comfortable everyday analogy, because nothing in your everyday experience behaves this way. And here's the critical part, the part that changes everything. For a wave to persist, to remain stable, to not immediately destroy itself through interference, it has to fit. The wave has to wrap around the nucleus in such a way that it closes back on itself perfectly, like a snake biting its own tail, forming a perfect unbroken loop. If the loop doesn't close perfectly, if the wavelength doesn't fit, the wave interferes with itself. It cancels itself out. It cannot exist in that configuration. Not won't, cannot. Which means only certain orbits, certain very specific distances from the nucleus, are physically permitted. Everything in between is not just unlikely. It is not just unstable, it is forbidden by the mathematics of waves themselves. This is the first reason the electron never spirals inward. There is nowhere for it to spiral to. The intermediate positions don't exist as valid quantum states. The electron can't fall to an orbit that the wave equation doesn't allow. It's not resisting, it's not fighting. There's simply no mathematical reality for it to fall into. But there's something even deeper, something even more shocking, something that, when I first worked through it carefully, made me genuinely laugh out loud. Not because it's funny, but because it's the kind of truth that hits you like a physical thing. Heisenberg's uncertainty principle. Now, most people have heard this name. Most people think it means something like, our measuring instruments disturb the thing we're measuring, like peeking at a sleeping cat wakes it up. That's not what it means. That interpretation is too comfortable, too familiar, too reassuringly tied to everyday experience. The uncertainty principle means something far more radical. It means that position and momentum, where something is and how fast it's moving, are not two separate properties that an object has, and that we simply have trouble measuring. They are fundamentally, irreducibly, at the deepest level of reality, complementary, linked, trade-offs built into the fabric of existence. The universe itself does not simultaneously contain both pieces of information. It's not hidden from us. It's not hiding anywhere. It doesn't exist simultaneously in definite form. Now watch what happens when you apply this to our electrons. Suppose the electron tried to stop. Suppose it tried to fall into the nucleus and just sit there, perfectly still, perfectly located, at rest. If it were perfectly still and perfectly located, you would know both its position and its momentum exactly. Position, right there in the nucleus. Momentum, zero. But the uncertainty principle says you cannot know both. If position is perfectly defined, momentum must be wildly, infinitely uncertain. And wildly uncertain momentum means wildly uncertain velocity. And wildly uncertain velocity means the electron is moving, energetically, unavoidably. The electron cannot stop moving because stopping would require the universe to simultaneously know where it is and that it isn't moving. And the universe, at its most fundamental level, does not work that way. So the electron has what physicists call zero-point energy, irreducible, unavoidable. Even at absolute zero, the coldest temperature physically possible, the electron is still moving, not because something is pushing it, because stopping would violate the logical consistency of space and time itself. The electron isn't just allowed to keep moving, it is required to keep moving. The universe enforces it, constantly, without exception. And then there's the other rule, the one that might be the most powerful single statement in all of physics. No two electrons can be in the same quantum state. Wolfgang Pauli discovered this, and like all the greatest discoveries, it sounds almost innocent until you start following its implications into every corner of reality. Think about what it means. Electrons can't just pile up in the lowest energy level, can't just all crowd into the most comfortable, most stable position. As more and more electrons fill an atom, each new electron is forced into a higher energy level because the lower ones are already taken, occupied, forbidden. This is why atoms have structure. This is why the periodic table exists. This is why carbon behaves differently from nitrogen, why iron has different properties from copper, why the chemistry that makes life possible can exist at all, because electrons are forced into different configurations, different energy levels, different arrangements. And those arrangements determine everything about how atoms interact with each other. And here's the part that should genuinely stop you for a moment. The reason your hand doesn't pass through this table right now, the reason solid objects feel solid, is not primarily because of the strong nuclear force or electromagnetic attraction. It's because electrons in the atoms of your hand and electrons in the atoms of the table cannot occupy the same quantum states. They resist, they push back. Not because of some force in the conventional sense, but because the universe simply doesn't contain a version of reality where they overlap. The solidity of the world, the concreteness of everything you touch and stand on and build, is the Pauli exclusion principle expressed in everyday experience. Now let me pull all of this together, because I don't want you to walk away thinking this is just a collection of interesting quantum curiosities. I want you to see what it actually means. Every atom in the universe is stable, has been stable for billions of years, not because of some gentle, forgiving process that could have gone differently. It's stable because of a series of absolute, non-negotiable constraints built into the structure of reality at the most fundamental level. Constraints that don't bend, don't negotiate, don't have exceptions. Electrons don't lose energy because they cannot exist between energy levels, because waves cannot form in forbidden spaces, because the uncertainty principle requires unavoidable motion, because the exclusion principle forces them into distinct, stable configurations. It's not one reason, it's a conspiracy of reasons, each one remarkable on its own, each one reinforcing the others, that together produce the single most important physical fact in the universe. Matter is stable. And because matter is stable, chemistry works. Because chemistry works, biology works. Because biology works, evolution works. Because evolution works, consciousness emerges, curiosity emerges. The ability to ask, why does the electron not lose its energy, emerges. The electron's stubbornness is the universe's gift to complexity. And here's the final thing, the thing I find most beautiful of all. When human beings figured this out, when they finally developed the mathematical framework to understand why electrons behave the way they do, they didn't just answer an academic question, they unlocked the entire technological world you live in. Transistors work because of quantum energy levels. Lasers work because electrons jump between energy states in predictable ways. MRI machines map your body because of quantum spin states. Solar panels convert light to electricity because of quantum photoelectric effects. The computer, the phone, the medical scanner, the fiber optic cable, all of it, every last bit of it, is applied quantum mechanics. The question, why doesn't the electron lose its energy? That question, pursued far enough, gave the human race its most powerful technologies. Not because anyone was trying to build technology, because people were genuinely, passionately, irresistibly curious about how the universe actually works. And that curiosity, that refusal to accept comfortable, familiar, incorrect answers, is the most human thing there is. The electron refuses to lose its energy, and in doing so, it makes everything possible. Maybe there's something to learn from that. What if the universe has been trying to teach us something this entire time? Not in textbooks, not in equations, not in laboratories alone, but in the very act of existing. Every atom around you, every molecule in your body, every solid surface you've ever touched is a daily demonstration of nature's most extraordinary commitment. Electrons hold their ground. They don't spiral. They don't collapse. They don't surrender their energy because the universe's own logical architecture makes surrender impossible. And that should mean something to you, not just as a scientific fact, but as a way of seeing the world. Reality, at its deepest level, is not fragile. It is not accidental. It is not barely holding together. It is built on rules so precise, so absolute, so beautifully interlocking that the stability of every atom is not a lucky accident. It is a mathematical inevitability. The classical world told us atoms should collapse. The quantum world showed us why they never will. And in that correction, in that beautiful, humbling upgrade to our understanding, we didn't just fix an equation. We discovered that the universe is far stranger, far more structured, and far more magnificent than anyone had dared to imagine. So the next time you touch something solid, breathe air, watch light travel across a room, know that you are witnessing the uncertainty principle in action, the exclusion principle standing guard, wave mechanics doing its quiet, essential work, billions of electrons in billions of atoms, all simultaneously obeying rules written into the geometry of space itself. That's not just physics, that's the universe being exactly as extraordinary as it truly is.